Hello, guys. This is Math 1200. This will be our first section, 1.1. And chapter 1, we're just going to do some review about algebra and some algebra. So, first section of chapter 1, we're going to look at what is a function. So, a lot of you may have heard this before in your math classes on this term function. So we're just going to go through it fairly quickly on uh, introducing a function, or for most of you, it should be a review. All right, on the top, we have the definition. A function is a rule that takes certain numbers as input and assigns uh, to each a definite output number. The set of all output number is called the domain of the function, and the set of all resulting output numbers is called the range of the function. All right, so here we have a quick example. We have some quantities such as date or discrete. Right? Discrete is the first thing that we have here. It means you can assign a specific number to it. Right? For example, you're either on day 1 or day 2 or day 3 or so on. Right? That's what discrete means. Meaning they take only a certain isolated value. Dates must be integers. Other quantities, such as time, are continuous as they can be any number. Right. So let's do give you guys a quick example. Right. So for discrete, right, some example would be like your age. Right. You have to be either 10 years old or 11 years old or 12 years old, right? Usually when we talk about age, we don't talk about like 10.5 years old, right? It's either 10 or 11. Of course, you can count in months, but that's going to be a little more complicated. Right? Some example of continuous would be something like your height, right? Maybe you are 5'11", right? But most of the time, you are not exactly 5'11". Maybe there's a little more to it, right? Or you say that, for example, for me, I'm 175 centimeters tall, right? But maybe I'm not exactly 175 centimeters tall. Maybe I'm 175.0023 and da da da. And so height is can be counted as a continuous variable because they can take on any number. Right. Now let's go back to our definition here. Let's look at domain and range first. Right. So a function, you can think about it as like a machine. Right. Right. And then the stuff that you put into the function, right, is called the domain. Right. And then after you put something from the domain into the function, it will spit out another thing, and that's called the range. All right. So, kind of a example would be like if you put a tomato, right, into some machine, and it gives you ketchup, right? K for ketchup. So this function would perform the work of maybe pressing the tomato and maybe cooking it, adding sugar, right? So function can be anything, right? You put something in and it spits something out. Now, since we're in a math class, right, the function that we're talking about mainly works with numbers, right? So domain are the numbers that you put in, and the range are the numbers that we get from this machine right here. All right, so let's take a look at this. Table 1.1, daily snowfall in inches for Boston from January 27th to February 9th. Right, so all these days, right, these are our domain, right? So if we want to find out how many, what's the number of inches of snowfall in any given day, right, we can refer to this table. So let's say I want to look at day 7, right? Day 7 right here, right? That's going to be our input, right? And then you look at the bottom, right? We get 16.2. That means on day 7, we have 16.2 inches of snowfall, right? And that's going to be your output. Oh, I forgot to put range here, range for snowfall. All right, so the domain is the number of days that you select or you select as an input into the function. And snowfall is going to be the range. It's going to be the collection of number that your function is going to spit out. Right? So you can pick any given day, and this table as a function will give you the snowfall in inches. Okay, so if you select another one, let's say 11, right, it gives you 0 inch of snowfall. All right, so no snowfall at all. All right, so next, let's talk about mathematical modeling. So here we have an example. So let's just take a look at this together, right? So we have snow cricket. All crickets chirp at essentially the same rate if they are at the same temperature. That means that the chirp rate is a function of temperature. In other words, if we know the temperature, we can determine the chirp rate. So I'm gonna stop here for a second. Uh, we know the relationship between the chirp rate and the temperature. So that means we can build a function that tells us the relationship between these two quantities. And that's the idea of mathematical modeling. We try to come up with functions that can help us predict some volume, right? So to give you a quick example, let's say we have um, age versus blood pressure. Right? So a lot of medical experiments will tell us that age has some relationship between blood pressure, right? So we can find out, we can build a function or discover a function that can help us relate the correlation between age and blood pressure. So for example, let's go back to our example here. The C is the chirp rate per minute. Steady temperature T, capital T, that's degrees in Fahrenheit, can be computed to a fair degree of accuracy using the formula right here. Okay, so C for chirp rate, that's a F parentheses of capital T, right? So this is the notation of functions, right? Right? F parentheses of T. This is red F of T, right? Where F stands for function and T is our input or our domain, right? Whatever our domain is going to be. In this case, is temperature, right? So it tells us that the relationship between chirp rate and temperature is 4T minus 160, right? So you get a temperature, you multiply by 4 minus 160, and that tells you about the chirp rate. All right, so we'll take a look at this in the next slide. Let's look at function notation. Right, so we write y equals to f of t to express that the fact that y is a function of t. The independent variable is t, right? So here another key term is the independent variable. That usually means our domain, right? So independent, or what do we use independent instead of domain? So we use independent variable because that's the variable we have freedom over, right? We get to pick what value we want for t, right? Now, in a lot of cases, we will just use t as a variable, but here we are talking about independent variable, means we can select the time or the temperature in this case that we want in order to find out what the chirp rate is at that exact temperature. The dependent variable is y, and f is the name of the function. So dependent variable means it depends, this y value depends on what we picked for t, right? So let's say if y is equal to t minus 1, right? So we can pick t. Let's say I want to pick t equals 5, right? If we pick t equals to 5, what is y, right? Y is going to be 5 minus 1, which is 4, right? So y is going to be the dependent variable, and y is equal to 4 when t is equal to 5, right? That's what it means um, to have independent variables and dependent variables. Okay, let's look at the second part. The graph of a function has an intercept where it crosses the horizontal or vertical axis. Horizontal intercept are also called the zeros of the function. Okay, so let's give you a quick graph and say I have, that's x, that's y, right? And then we have a line going through it, let's say this thing, right? So when it crosses the horizontal axis, which is the x-axis, this value, that's going to be your horizontal intercept, or the x-intercept, right? And when it crosses the vertical axis, that's going to be your y-intercept, right? Intercept and x-intercept. Okay, and the x-intercept is also called a zero. Right? And we'll talk when we solve function for zeros. This is essentially what we're looking at. All right. So next we have example 1. Graph the cricket chirp rate at the function f of t is equal to 4t minus 160. Solve f of t equal to 0. Interpret the result. Right. So to graph, you can simply make a table of solutions. Right. T and then c. Right. You can pick your value. Let's say I want to do 0 and 1, right? So now that's a bad choice. Let's say 40 and 100. Okay. So we pick temperature to be 40 Fahrenheit and 100 degrees. Those are our independent variables t, and then we just take these two values, plug in here, right? So 4 times 40, right? 4 times 40, 160 minus 160 will give you 0. 4 times 100, that's 400, minus 160 will give you 240. Right. So essentially what we're saying here is that when temperature is 40, we get 0 chirp rate. When temperature is 100, we get 240 per minute chirp rate. Okay? And then you just plot those 2 points on the plane and maybe about here, and then just connect these 2 points with the line. And that's how you get the graph, right? Part B, solve f of t equal to 0 to gives the horizontal intercept, right? So we actually found it here, it's a 40, but in order to solve for 0, first you just set the whole function, right? 4t minus 100 on up top here equal to 0, and then you will get this equation right here. 4t minus 160 is equal to 0, and then you just go ahead and solve it. You get t is equal to 40. Right, so at temperature of 40, chirp rate is 0. For temperature below 40, the model would predict negative values of c, so we conclude that the model does not apply for such temperature value. Right, so this is an interesting question to look at. Right, so if we extend the line further down here, that means we get negative chirp rate, right? But is it possible for crickets to chirp negatively? right? So if you chirp once, that's +1. It's impossible to get negative chirps, right? So in this context, we negative chirp rate would not make sense. So in this case, we are going to ignore any temperature below 40, right? Assuming if it's below 40, it's too cold and they're all dead, so they cannot chirp, right? Then, I mean, that kind of makes sense, right? All right, and another property of functions is we can talk about increasing or decreasing, right? A function f is increasing if the value of f of x or the y value, right? So you can um, look at this as like the y value, right? Oops, right? That's f of x or y, and then that's your x value, right? So if x increases, f of x increases, that will be increasing. If f decreases as x increases, then the function is decreasing, right? So one way um, I like to talk about increasing and decreasing is think about you're standing on top of a line and you're always traveling to the right. Do you climb uphill or downhill, right? So in this case, when you travel to the right, you're going up, right? Up this way. So it's increasing, right? But if you're standing on this line and you are traveling to the right, you're going downhill, right? So that is decreasing. I remember to determine increasing or decreasing, just travel to the right. All right, next 1.2, we're going to talk about linear functions. So before we move on, let's talk about these two terms, right? Linear and function, right? So functions we already know from 1.1, right? What does linear mean? So linear is the word line in it. So, it has to do something with the line, but does the line look like this? Does it look like that? Or does it look like this? Right? Crazy line. Right. So in the mathematical terms, when we talk about linear, we talk about that we mean first degree. Okay. So what does first degree mean? Let's take an example. Right? Let's say I have a polynomial x to the third power plus 4x squared minus 5x plus 11. Right, so that's a polynomial. When we talk about degree, we look at the highest power of x in this polynomial, right? So the highest power of x is 3, okay? That means this is going to be a third degree polynomial, right? So when we talk about linear, we only talk about first degree. An example of first degree will be like 3x plus 4, right? Where the power of x, if it's not written, it means it's to the power of 1, right? And taking into the function, we can write f of x is equal to 3x plus 4, right? That's what it means for it to be linear. And next, let's look at some examples. All right, example 1. If y is the world record time to run the mile in seconds, and t is the number of years since 1900, then record shows that approximately y is equal to g of t is equal to 260 minus 0.4 t. Explain the meaning of the intercept 260 and the slope negative 0.4 in terms of the world record time to run the mile and sketch the graph. So let's just look at the solution real fast. The intercept 260 tells us that the world record was 260 seconds in 1900, where t is 0, right? So let's look at the question again. The question says since 1900, right? So that's the first time that we're calculating mile time, right? So 0 is going to be your starting point, right? So the first ever recorded mile time is 260. So t does not necessarily mean time. In this case, it means years since 1900, and also says in here years since 1900, right? So if we are in 1900, then t would be 0 because we are 0 year after 1900, right? And right, so that's where your y-intercept means. The slope, negative 0.4, tells us that world record decreases at a rate of 0.4 seconds per year, right? So since the rate is negative, it means decrease, right? So remember that slope is rise over run, right? It means, oops, not run, a little too early for that, right? Rise over run. It means when you travel to the right by 1 unit, how many unit do you increase? Do you go up or go down? So when it's 0.4 or 0.4, it means when you go to the right by 1, the y value goes down by 0.4. Right, that's what negative 0.4 means. Now, if it were positive 0.4, then instead of going down by 0.4, you would go up by 0.4. Okay. All right, and here is our formula for the slope, right? Rise over run, or delta x over delta y, right? So delta, this symbol delta means change, right? So what we're looking at here, delta y, oh, this is red delta. Maybe I should write it down as well. Right, delta y over delta x means the change in y over the change in x. Right, so here we have the formula f of x2 minus f of x1 over x2 minus x1. Now, in algebra class, usually they write y2 minus y1 over x2 minus x1. Right, so here we have a really nice graph of looking at it. Right, the first point we have f x1 and f of x1. Second point we have x2 and f of x2. Right, to find the slope of the straight line that goes through these 2 points, we first find out how many units do we run to the right by doing x2 minus x1. Right, x1, x2 minus x1. And then how many do we rise by taking f of x2 minus f of x1. And then you just divide these two numbers to get the slope. All right, so here we have the formal definition of a linear function. A linear function can be put in slope-intercept form. Y is equal to f of x, or is equal to b plus mx. More commonly, you will see y is equal to mx plus b, right? Where m is the slope, or a rate of change of y with respect to x. Right? Or another way to say this is delta y and delta x, right? Delta y over delta x. That's the formula for the slope. And b is the vertical intercept, or the y value when x is 0. Right? So b is the vertical intercept. The equation of the line of a slope m through the point x0, y0 is this. Right? Now, this form is called the point slope form. Okay, and these two are the most commonly used equation for linear, right? The slope intercept form, mx plus b, or the point slope form. All right, so problem 9, this is an interesting exercise. We have 4 lines given by equation y equals to b plus mx, which is the slope intercept form. Okay, match the lines to the condition on the perimeter m and b. Now I'm gonna do one with you, and then you can pause the video to try to figure out the rest. All right, so m is greater than 0, that means m is positive, and b is positive, that means intercept positive. All right, so m is slope, and b is y-intercept. Right, so let's talk about this. If slope is positive, it means it's increasing. Right, if slope is negative, that means it's decreasing, right? Remember, increasing and decreasing means increasing means you're walking up as you're traveling to the right, and decreasing means you're going down as you're traveling to the right. All right, so let's look at the first one. M is positive, that means you're traveling up as you're going to the right, so it's either line 1 or line 2. Right now, y-intercept is positive, right? So we look at these two lines and where the lines crosses the y-axis, right? So if you look at L2, line 2, it crosses y-axis right here, but here the y value is negative because it's below the x-axis, right? So it's not going to be line 2 for A. That leaves us line 1, right? Line 1 has positive slope, right? And it crosses the y-axis right here, which is above the axis. That means B is positive, right? So for part A, we have line 1. Go ahead and pause the video and try to figure out the rest on your own. All right, here we go. For part B, we have line 3. All right, line 3 is decreasing, positive y-intercept. Part Oh, that's part B, and part C is positive slope and negative intercept, right? So that'll be our L2. My bad, that was a mistake. All right, so L2, positive slope, negative intercept, and last but not least, part D, we have negative slope and negative intercept. That's going to be L4. All right, so here's another exercise. Go ahead and try this one on your own. All right, part A, the two lines that have the same slope are L2, line 2, and line 3. And of these two lines, which has a larger y-intercept, right? So the one that's a little higher, right, which is the L2, the y-intercept is right here for L2, whereas for L3, the y-intercept is right here. Right. Next, which two lines have the same y-intercept, right? So you look at the y-axis and see where two lines crosses the same point, and we get this point right here. So the lines that goes through this point are line 1 and line 3, right? So line 1 and line 3 have the same y-intercept of these two lines, which has the larger slope, right? So larger slope means you're going up faster, right? So which line is going up faster, line 1 or line 2, right? When you're traveling to the right? So line 1 is going up really fast, very slanted, right? So line 1 has a larger slope. Next, let's look at how we can recognize data from a linear function. Right, so remember a linear function has a really fixed property, right? So one easy way to do this is by doing graphing, or if you want, you can identify the difference, right? So let's first identify the difference. So notice that we have a table, we have X and Y rows. So X is that's our domain, Y is our range. So let's look at the change in X. Right, so to go from 0 to 1, we added 1, right? So 1 to 2, we added 1. So from 2 to 3, we added 1. Right, so that's fixed. That's very nice. Let's see if the y values are fixed. Right, to go from 27 to 25, that's minus 2. 25 to 23, that's minus 2. 23 to 21, that's minus 2 as well. Right, so notice that the change in x value and the change in y value, they are fixed, right? They're always plus 1, plus 1, plus 1 for x, and minus 2, minus 2, minus 2 for y. So yes, this is linear. Okay, so go ahead and try the other two. All right, so for part B, t is being plus 5, plus 5, plus 5. That's good. Let's look at the dependent variable s. Okay, so that's what, plus 10. That's plus 10. That's plus 10. Okay, so that's pretty nice as well, right? Very fixed, very stable. They're all the same. So yes, that's a linear as well. And part C, that's plus 1, plus 1, plus 1. and the dependent variable is going to be +5, +8, and +10. Right, so this is where we see, okay, the x value or the independent variable u is increasing steadily, right? Always adding 1. But the dependent variable w is not steady, right? Adding 5 and then 8 and then 10, right? It's like it's going increasing faster and faster and faster, right? So no, this is not a linear function. All right, let's look at our last example. All right, problem 30. Annual sales of music compact discs or CDs have declined since 2000. Sales were 942.5 million in 2000 and 384.7 million in 2008. First, find a formula for annual sales. S in millions of CDs as a linear function of the number of years T since 2000. Okay, so let's make a table. We have T and S. Okay? T for time and S for sales, right? And be very careful. T is the number of years since 2000, right? So the year 2000, it's going to be 0 because that's when we started counting, right? So year 2008, that's going to be 8, right? Because 2008 is 8 years after 2000, right? So T is 0 for 2000, 8 for 2008, right? The number of sales in 2000 is 942.5. And the sales in 2008 is 384.7. All right, so T, that's going to be our independent variable, and S, the sales, that's going to be our dependent variable. Now, we need to figure out a linear function, right? So let's use the point slope form, right? Mx plus b, right? So we need to figure out what m is and what b is. So first, m is y2 minus y1 over x2 minus x1, right? So we can just take those in, right? So y2, those are going to be our dependent variables. Let's do 384.7 minus 942.5 over 8 minus 0. Now, it actually doesn't matter which one you pick first, as long as you're consistent between your variable x and y. So if you want to put 384.7 first, then you have to put a first in the denominator. If you want to put 942.5 first, then you have to put 0 first. Either way, you will get the same value. All right, and you get negative 642.2 over 8, and you can punch that into a calculator. And that's going to be negative 80.275. Okay, so we get m. Now we need to figure out what b is. So b is the y-intercept, and to find y-intercept, we just need to set x equal to 0, right? So when time is 0, time is 0, number of cells is 942.5, and that value is going to be your b, right here, b. So your function will look like S, number of sales, is equal to M, that's negative 80.275 times T, right? Time, number of years after 2000, and then plus B, the y-intercept, which is 942.5. Okay, right? So that's part A. Part A. Right, now part B, let's see. Give units for and interpret the slope of vertical and the vertical intercept of this function. Right. So slope is negative 80.275. Right. And what does that mean? Right. Negative 80.275. So t is the number of years. That means as we go on a year, right, when year increases by 1, the CD sales is going to decrease by 80.275 million, right? So negative 80.275 CDs per year, right? The negative means the sales of CD are decreasing, and a vertical intercept, which is B, which is 942.5. That's just the CD sales, right? Uh, in year 2000, right? That's the initial point that we were looking at. Okay. All right, now let's look at part C. Use the formula to predict music CD sales in 2012, right? So we want to find out uh, number of sales in 2012. So first we need to figure out T, right? So in year 2012, how many years is that after the year 2000? That's right, it's 12 years. That means T is going to be 12. That means we need to take this number 12, plug into the function that we had from part 1, and we will find our sales. So sales is equal to negative 80.275 times 12 plus 942.5. And you can plug that into the calculator. We get negative 28.8. Okay. So let's talk about this number for a sec. First, does that number make sense? Right? Negative 20.8. Think about the context of the problem. What does this value represent? S represents the sales, right? In this case, sales in 2012. Now, is it possible for the sales of numbers of CD to be lower than 0, right? Can you sell negative CDs, right? Maybe if you were the seller and you buy CD, maybe that'll be negative, but in this context, it doesn't make sense, right? You have extra CDs that you didn't sell, but you cannot sell negative CDs, right? So, using this formula or this model, right, we can call that a model to predict future CD sales. Is this a good model? Right? This is a good model to predict number of CD sales since the year 2000. Now, I know I still buy a CD now and then, so it cannot be possible to get negative, right? Maybe not 0, but there are still some CDs sold even now, right? So this would not be a good model, right? No, not a good model, because it's not accurate. Maybe it's accurate within a few years, right? Between 2000 and 2008, maybe up to 2010, maybe that's a good model, but it's not a good model in long term, right? For example, in the year 2100, right? Maybe CDs are still around, right? You never know, right? So this is a simple example of a model or mathematical modeling, right? But it's not a good model, but it works sometimes, right? Maybe rarely. Okay. All right. So that's all for today. 1.1 and 1.2. Make sure if you have any questions, please come on by my office hour on Zoom. The link is available on Blackboard, and I'll see you next time.